Hi everyone, Mr. Boltri here, bringing you video 7.2. We're going to be talking about how to make energy flow diagrams. First, we're going to talk about a very important concept called conservation of energy, and then I'll take you through 3 examples of how to make energy flow diagrams applying conservation of energy. Conservation of energy relies on the idea that energy cannot be created or destroyed, but it can be transferred from one type of energy to another type of energy or from one object to another object. So if we were to write this in equation form, we could say that the energy in a system or in an object at the beginning is going to be equal to the energy in that object or in that system at the end, plus or minus any energy that goes in or any energy that comes out. Obviously, any energy that went in is going to be plus and any energy that goes out is going to be minus. But in these really early examples, we're going to say that this energy in and out, we're just going to go ahead and set that to be 0 to kind of simplify the problems. We're going to say no energy enters, no energy leaves. So then the equation is quite a bit simpler. It's just the energy at the start is going to be equal to the energy at the end. It's going to be a totally, if we have 4 energy over here, we're going to have 4 energy over there. We'll deal with more complicated problems where energy enters and leaves later in the unit. But for right now, we're going to set this to be 0. So all the energy at the start is going to be equal to all the energy at the end. Okay, so then what this looks like in an energy flow diagram. So if we're given a situation, for example, this situation is a wind-up toy. It's wound up tightly at the beginning and then released, and it speeds up along a level surface. And now let's track the energy flow in this circumstance. So in our last class activity, we actually wrote down all the energy involved in this situation. So when a wound up toy is tightly wound, there's a lot of elastic potential energy. And we can see by these arrows that the kinetic energy is getting bigger and bigger and bigger. So this is actually how we're going to be tracking the flow of energy in a circumstance. You see, I've listed out my types of energy at the bottom: kinetic energy, elastic potential, gravitational potential, and dissipated. Sometimes you'll also see chemical potential in these tables as well. But since we know that there's no chemical potential energy in a wind-up toy, I just didn't even put that in the diagram. So the first step is make sure you've identified situation A, B, and C, so you know exactly what situations we're going to be making the energy flow diagram for. And then the next thing I like to think about is what kind of energy am I certain is acting in this problem? So for example, I've circled my kinetic energy in both A, B, and C, because I can see that these velocity arrows represent the object is moving. If the object is moving, then there's definitely going to be kinetic energy in all of those circumstances. And then I also know, because it's a wind-up toy, that there's elastic potential energy. And I know for sure that there's elastic potential energy in A and B, and there's a chance it's run out of elastic potential energy in C. By the time it gets all the way to C, it's done speeding up. So I didn't circle it in C. So once you've identified all the energy that you're certain is part of the problem, the other thing you can do for these problems is to cross out any energy you're sure is not part of the problem. So since I see that it's not going up, up, up at all, I can go ahead and cross out all of my gravitational potential energy. And then you're getting pretty ready to start to make your energy flow diagram. To make your energy flow diagram, I'm just going to choose an arbitrary amount of energy to start at the beginning with. I've chosen 1, 2, 3, 4, 5 blocks of energy to be in situation 1. This is an arbitrary choice, and we know that energy is not actually measured in blocks, but we're just going to use blocks as a visual representation of energy until we actually get down into the nitty-gritty of knowing exactly the numbers involved in energy. So this just represents 5 units of energy. So we know by the law of conservation of energy that if we have 5 blocks, 5 units of energy at the beginning, we need to have 5 units of energy in the middle and 5 units of energy at the end. Because in this circumstance, no energy is entering or leaving my bunny system. So I've chosen 5 blocks of energy. I put a little in kinetic energy because I can see that this arrow is very small, but I put most of it in elastic potential energy because I know my toy is very tightly wound. So then the next thing I want to think about is, how did that energy change from situation A to situation B? Well, I know that I see the velocity arrow got bigger, so it got faster. So I know there must be more kinetic energy. And then where did that kinetic energy come from? Well, the toy was tightly wound, but as it is unwinding, it's speeding up. So I took my elastic potential energy and I made my elastic potential energy smaller because I know the toy is unwinding, which is causing it to speed up. So you see, still I have 1, 2, 3, 4, 5 blocks of energy, but my elastic potential energy is lower and my kinetic energy is higher. Moving into situation C, I am just making an assumption that the elastic potential energy is all run out. But if you still left one block here, that wouldn't be wrong unless the problem says the toy is totally unwound. But definitely the kinetic energy, it has increased, because if we compare the velocity arrows, we can see that the velocity arrow in C is bigger than the velocity arrow in B. So make sure that your kinetic energy increases. So as you can see, this is kind of an arbitrary process. You could have chosen 6 blocks at the beginning here, or you could have left 1 block in the elastic potential energy at the end, unless it said otherwise. So with these problems, there could be possibly multiple correct answers. The most important thing to think about is how the energy is changing over time. So if I were to be grading this, I would be looking for the kinetic energy to be going up, 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 and the elastic potential energy to be going down, down, down. And you might be thinking, well, how do you know that there wasn't dissipated energy? In this circumstance, I might make a note that there wouldn't be dissipated energy just to simplify the problem. Or if you had included dissipated energy, that could be correct as well. We're going to do a problem later where we do include dissipated energy. But again, just to kind of run you through this process so you can see multiple examples. And then in our next class, we're going to do a bunch of these. I have 4 pages of practice problems involving this exact type of energy flow. So in this circumstance, again, I see kinetic energy because I see my velocity arrows. And also, since the bunny is getting higher and higher and higher, I also know that there's going to be gravitational potential energy. I'm also noticing that it's still a wind-up toy, so there's going to be elastic potential energy as well. So I'm going to, again, make sure I identify my A, my B, and my C, and then circle the ones that I know are going to be there. So my kinetic energy, which I see in my velocity arrows. I also see elastic potential energy because it's a wind-up toy. And again, I'm assuming that it's probably fully unwound by the end of the problem, which is something that if there were to be text description with this, that would say. And you'll notice I have no gravitational potential energy at the beginning because it's kind of at the bottom. But then as it gets higher and higher, I've circled my gravitational potential energy. And again, in this problem, I'm just going to assume that there's no dissipated energy because that complicates the problem quite a bit, but we'll get to that in a future example. So again, I've chosen 5 blocks at the beginning. Again, that's kind of an arbitrary choice. You could choose 4 or 6. I would try not to choose too many just because then it kind of becomes hard to track all those. Because remember, if I have 5 here, I need to have 5 here as well and 5 here as well. So I kind of try to keep it to be a little bit of a small number. I find that 4, 5, and 6 tends to be an okay number to be able to track all the energy. So I have a little bit of kinetic energy, and then most of it is wound up in the wound up toy and the elastic potential energy. So I noticed that my velocity arrows are not getting bigger or smaller. So in my next example, I'm going to still have 1 block of kinetic energy. But I noticed that I got higher. So I'm going to have my gravitational potential energy be greater. And where did that energy come from? Well, that means that probably the toy was unwinding. So that elastic potential energy is going to be less. The same pattern continues as the toy continues to unwind, 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 causing the object to get higher and higher on the ramp, increasing the gravitational potential energy as the kinetic energy stays the same. So this is another energy flow diagram with, again, multiple correct answers. But the important thing that I'm looking for when I'm looking at this is that the kinetic energy stays the same because I can see my velocity arrows are the same. The elastic potential energy is going down, down, down every time. And the gravitational potential energy is going up, up, up. Well, let's do one more example and then we'll wrap up the video. And like I said, we'll do a lot more practice on this in our next class. So here we have a skateboard, which has a big velocity at the beginning, but seems to be slowing down as it goes along. So identifying my A, my B, and my C, we're going to have a lot of kinetic energy going down to just a little kinetic energy, but not quite 0. So I know there's going to be kinetic energy in all 3 of my answers. We see that it's not wound up, it's not a wind up toy or anything like that. So there's no elastic potential energy. It's not going up or down a hill. So there's no gravitational potential energy, which gets us to the only other energy that could be involved in the situation is going to be dissipated energy. So let me show you how that works. And by the way, some key indicators that, and you might want to write this down, some key indicators of dissipated energy are heat, light, and sound. I'm actually going to repeat that because I think it's really important, and I'm sure I'll say it in class as well. But some indicators in a problem that I would like for you to include dissipated energy is if you see anything about heat, light, or sound. And I'll let you know if in a certain problem you can ignore dissipated energy. Like in those previous problems, I ignored dissipated energy, and probably I was able to do that because somewhere, again, if there was a sentence associated with the problem, I would have said ignore dissipated energy. But in this one, obviously we cannot, because if I have 4 blocks of kinetic energy at the beginning, It would be impossible for me to have 4 blocks of kinetic energy in situation B, because that would show that it's moving at the same velocity, and I can see very clearly that it's moving at a smaller velocity. So in situation B, you notice I have 3 blocks of kinetic energy, which means that the only thing that could have happened is one of the blocks went to dissipated energy. And the same pattern continues in part C, where the kinetic energy continues to go down and the dissipated energy continues to go up. One example kind of question that I would love to ask is, what do you think that situation D would look like? I think in situation D, the kinetic energy would continue to go down, dissipated energy would continue to go up until the skateboard comes to a stop. And so actually we could prove this, or we could show this, we could make this make sense, because if you listen to a skateboard sliding along, you're probably going to hear it rubbing against the ground, causing friction. And actually, if you feel the wheels, then they're actually going to be quite a bit warmer. So like I said, dissipated energy we can see in heat, light, and sound. And in a skateboard slowing down and as it slides along, we see quite a few of those. So this is a third example of how we're going to be doing energy flow diagrams. This is a really important skill that allows us to track how much energy there was at the beginning. If there's 4 blocks here, we still need 4 here and 4 here. Again, we're going to simplify the problems and say no energy is going into or out of the skateboard during this whole process. And we'll work with energy entering and leaving systems later in the same unit. We're going to do more practice on this in our next class, 4 pages, like I said, but just make sure that you have wrapped your head around the very basics of the concepts. Feel free to watch this video again, and I'm happy to answer your next questions. But for now, this is Mr. Boltri wrapping up video 7.2. Go Bears.